If I look at the pressure volume diagram of a mixture of two components, as we said this time, if we are at the high pressure and we have all liquid, as we increase the volume, so we change the volume slightly, the liquid pressure drops significantly till we hit the bubble point. But since this time we have a mixture of two components, the pressure will not stay constant. So if we continue dropping the pressure by increasing, if we continue increasing the volume, the pressure continues to drop as we convert liquid to the gas. So the pressure drops as we convert liquid to the gas till we convert all the last droplet of the liquid to the gas, and that's our dew point. And after that, we have a gas phase, increasing more volume, the gas will expand more. So there will be three distinct behavior. One with a very high slope, that's where we have liquid till we hit the bubble point, and then with the second slope, and then with the third slope, which is the gas. So we have liquid, liquid plus gas, and the gas zone. So if we perform this experiment at different temperatures, okay, so if we do this at different temperatures, we can have these graphs, these pressure versus volume graphs at different temperatures, and then we can connect all the bubble points, we can connect all the dew points, and we can generate these phase envelope. So the difference is in the case of mixture of two components, this way these lines are not parallel to the horizontal line, which means the bubble point is different than the dew point is different than the vapor pressure. However, in the case of pure components, these lines, they were parallel to the horizontal line, which means the dew bubble point was equal to the dew point equal to the vapor pressure line. Okay, so this is the major difference between the mixture of two components and the single component. Generally, what we do, I could give this as a true false questions. Sometimes I give this graph and I say, hey, this belongs to the mixture of two components, true or false. So you look at this vapor pressure lines, these are not parallel to the horizontal line. Bubble point pressure is different than the dew point pressure. Definitely, this is the mixture of multi-component. If these lines were horizontal, then you know that's the pure component. Sometimes also I'll give this graph and I say, hey, at 400 degree Fahrenheit, what is the liquid, saturated liquid, and saturated gas densities? Okay, so if I give you this graph and I say, what is the saturated liquid and saturated gas densities? We know at the bubble point, the liquid is saturated because if I change a little bit of the pressure or volume, the liquid starts converting to the gas. Okay, so it's saturated with the gas, cannot hold more gas in it. So you drop a little bit of pressure, the gas is going to come out. So this point, I have a saturated liquid. So I can read what here we have is a specific volume of that liquid. So at 400, if I ask you to find the density of the saturated liquid at 400, so you look at the bubble point, you read the value. So this is a specific, remember, this is a specific volume. A specific volume is 1 over density. This is cubic feet per pound. So to find the density, you use 1 over this number, and that becomes the density of the saturated liquid. For the saturated gas, we know at the dew point, we have the last droplet of liquid. So it's a gas, it's a saturated gas. If you increase a little bit of pressure, then you start having more liquid. If you drop a little bit of pressure, you start having more liquid. So at this point, the gas is saturated. So the gas is saturated, therefore, to find the density at that point, I just draw a line, I read the specific volume, 1 over that is the density. If I ask you to find the saturated liquid and gas densities at 454, we know that's a critical point. So at the critical point, the gas and liquid coexist. So there will be only one density for gas and liquid. Okay. So these are kind of a concept questions that you might expect for your quiz or for your closed book part of your exam. Okay. So another graph that we are interested is the pressure versus composition. Now that we have two components, more than one component in our mixture, we also wanted to know the state of the phases, quantities, and compositions of gas and liquid at different pressure and temperature conditions, and different pressure and composition conditions. Okay. So this is a pressure composition diagram, which is basically we plot pressure versus the composition of one of the components. We know it's a mixture of two components, so 1 minus the percent of A, if I have like 50% A, 1 minus that is B. So we have 50% A, 50% B. If I have 20% A, then I have 80% B. So we plot pressure versus the composition of one of the components. And then for that mixture, let's say the mixture of 20% component A, therefore 80% component B, we can find dew point pressures and the bubble point pressures. We can repeat these calculations for different mixtures, and we can generate this two-phase envelope, okay, which basically falls between the bubble point line and dew point line, okay. In this case, for the mixture of two components, we can also use the definition of what we call equilibrium tie line. The equilibrium tie line is a line parallel to the composition line, okay, which basically connects the saturated liquid and the saturated gas at a specific pressure, okay. So we use this definition to come up with the quantities of gas and liquid anywhere inside the two-phase. I'll go over that with one example, which makes it much easier to understand. So this generally has been a closed book question every semester. So what it says find the compositions and quantities of gas and liquid formed when 3 pound-mole of mixture of 70 pound-mole percent methane and 30 pound-mole percent ethane are brought to the equilibrium at minus 100 degree Fahrenheit and 400 psi. So we are going to mix methane and ethane, okay? So what we need to do is to go to the book and find the pressure versus composition diagram corresponding to methane and ethane. And we know we are going to mix them at minus 100 degree Fahrenheit. So if you go to the book, the figure, let's say 223, shows different compositions, different phase envelopes for different mixtures of methane and ethane, okay? For example, this envelope in blue is a mixture of methane, different mixtures of methane and ethane at minus 100 degree Fahrenheit, so which basically corresponds to this example. Because we have a mixture of methane and ethane, so this figure 223 is for methane and ethane. We have temperature of minus 100 degree Fahrenheit, so this blue phase envelope corresponds to minus 100 degree Fahrenheit. Now that I identify my phase envelope, I need to see where my mixture is in this envelope. So the question says you have 70 pound-mole percent of methane. So this is pressure versus methane composition. So I go to the x-axis and I find 70% and I draw a line. So this is a 70% line. On this line, I have 70% of methane. And then it says the pressure is 400 psi. So this is pressure and this is 400. So I know on this line is a 400 psi. So 400 psi line intersects with 70% methane line at point 1. So point 1 is a point where I have 70% of methane at 400 psi and minus 100 degree Fahrenheit. Okay, so minus 100 degree Fahrenheit, that's my envelope. 400 psi, that's my pressure, and 70 pound-mole of methane. So point 1 is where my initial state of the mixture is. So at this point, I know I have gas and liquid because this point number 1 falls inside the two-phase envelope. Okay, if the pressure was, let's say, 900, okay, if it was 900 and 70 pound-mole of methane, then this point was like falling somewhere here to the left side of the bubble point. So it was all liquid. So the composition was 100% liquid, okay, and the 100% liquid, and the composition was 70% methane and 30% ethane. So 70% methane, 30% ethane at 900 psi and minus 100 degree Fahrenheit is all liquid. However, since this point is falling inside the two-phase, we will have gas and liquid, okay? So we need to know what is the composition of the gas and what is the composition of the liquid, and what is the quantities, how much of gas and liquid I have in point 1, okay? how much of gas and liquid I have at any one of these points. Okay, so to do that, what we are going to do, we are going to use the definition of the tie lines. So as soon as I find point number 1, okay, I'm going to draw a parallel line by the composition. So I'm going to use this tie line. I have point number 1. I know the pressure is 400. So I draw this line. This line intersects with the bubble point line at point 2 and dew point line at point 3. So point 2 is my saturated liquid, point 3 is my saturated gas. Okay, so at saturated liquid, composition of the liquid is, I can read the composition. At point 2, I have 52.2% of methane. So if I have 52.2% of methane at this saturated liquid, then I should have 47.8% of ethane at that point. Because remember, it's a mixture of two components. And in the liquid, the summation of the components should add, the composition should add up to 100. In the gas, it should add up to 100 as well. So 0.2 is my saturated liquid, 0.3 is my saturated gas. So at saturated liquid, the amount of methane is 52.2, therefore 1 minus that, or 100 minus that, which is 47.8, is a composition of the ethane. 0.3 is my saturated gas. So the composition of the gas is at 0.3. I have 91.8% of methane that I can read from the x-axis. 100 minus that is 8.2, which is the amount of ethane. So if I get the amount of methane at the liquid and at the saturated gas point, 100 minus liquid and 100 minus gas is the amount of ethane. So this way I can find the composition of saturated liquid and saturated gas when 70 pound mole percent of methane is mixed with the 30 pound mole percent of ethane at 400 psi and minus 100 degree Fahrenheit. So this basically gives me the composition of saturated liquid and composition of saturated gas. And composition at the point 1 is basically that 70%, 30%. So we have the composition at these 3 points. Now I need to know how much of mixture at this point 1 that I have mixture is gas and how much of that is liquid. I know at point 2 I have 100% liquid because that's a bubble point line. Okay. I know at point 3 I have 0% liquid because that's a dew point line. That's the last droplet of liquid converting to the gas. So here I have 0, here I have 100. How much I have at point 1? So it's simply the length of this part, 1, 3, to the length of 2, 3. I'm just using the proportionality. So at point 3, I had 91.8. At point 1, I had 70. So 91.8 minus 70, it's the length of this part, 1, 3. And then 91.8 minus 52.2 is the length of 2, 3. So 1, 3 divided by 2, 3 gives me the portion of the liquid at point 1. Okay, so it's very sometimes confusing. So some students, they make a mistake to divide which part by which part. But always, if you want to do something like this, think about the extreme cases. If the point 1 was very close to point 2, that means point 1 is very liquid saturated. It should be very high percentage of the liquid. So definitely this 3.1 should be divided by 3.2, because if you divide this part by the whole, you get a very much smaller number. Okay, so the same for the gas. At point 3 we have 100% of gas. At point 2 we have 0% of gas. So how much gas we have at point 1? So it's 2.1 divided by 2.3. So 2.1, the length of 2.1 is at point 1 I have 70. At point 2 I have 52.2. So 70 minus 50.2. And 91.8 minus 52.2. So that gives me the portion of the gas at point 1. These proportionalities, these are for 1 pound mole of mixture. But since you have 3 pounds of mixture, then you need to multiply this by 3. So we multiply that by 3. This is going to be the portion of gas and the portion of liquid at point 1. So I got the quantities of gas and liquid at point 1 and composition of saturated gas and saturated liquid in this table. Okay, so it's very important. You will have questions on the homework assignment to work with this, and definitely you will have this type of questions in